Okay, today's video is about uniform circular motion. Uniform circular motion is when we have a particle which is running around in a circle, and it runs around with constant speed. That's what the uniform means. Now, the question we should ask ourselves is, if it's going with constant speed, is it accelerating? And of course, before you took this course, you would have said no, because it's going with constant speed. But in fact, acceleration means rate of change of velocity, and this particle running around in a circle is not going with constant velocity, even though it's going with constant speed. So there are two ways that acceleration can happen. One way is you can change the magnitude of the velocity vector. That's changing the speed. And the other is you can change the direction of the velocity vector. And that's what's happening in uniform circular motion. The direction is the only thing that's changing. Now, we should have a little quick review about some of our kinematics and vectors. In particular, we need to remind ourselves what the definition of average acceleration is. Average acceleration is the change in the velocity vector divided by the elapsed time, which is normally denoted delta v over delta t. Again, keep in mind that delta v is a difference of vectors, not a difference of numbers. And also, instantaneous acceleration is what we get when we let delta t get extremely small. Now, I'll remind you what vector subtraction is. One of the ways that you can achieve the subtraction of two vectors is to place them tail to tail and draw the difference vector from the head of the first velocity to the head of the second velocity. Okay, so that's all we need in order to proceed with our examination of what is the acceleration. That's basically what this video is about. What is the acceleration of something which is traveling with speed v in a circle of radius r? So I've drawn here a circle of radius r, and I've shown you at two different times the velocity of the vector. So here's v sub 1, the first velocity. Here's v sub 2, the second velocity. So this is the velocity at time t1. This is the velocity at time t2. The important thing to keep in mind here is that v2 equals v1 equals v. This is not a vector equation here. This is a scalar equation. This is the speeds. The speed at time 1 equals the speed at time 2, and I'm just going to call that v, the speed of this particle. I've also constructed a triangle here, and delta theta is the angular distance over which this particle has moved from t1 to t2. And if I simply draw this line across here, that's what you'll recall is called the chord of between these 2 points on the circle, which I call that delta c. During this time, the particle has traveled a path, which is this arc right here, and I'll call that delta s. So we have a triangle here. Delta theta is here. It's an isosceles triangle. These two sides are equal, and its base is of length delta c. Now I'm going to take this velocity vector and move it down here, and I'm going to take this velocity vector and move it down here like this, so that I can construct delta v. Now, the first thing you should notice here is that delta v, depending on where you draw it from, is pointing sort of toward the center of the circle. You can't really say where exactly it's pointing to, because you don't know whether to draw it here or halfway between or whatever. But at any rate, the important thing is that it's in general pointing into the circle, not out of the circle. And I can think that you can see that suppose we say let's look at the middle of the arc length here and draw it there, that as you get that arc length gets smaller and smaller, this vector is going to get more and more pointing toward the center of the circle. Okay, so let's look at what we have here now. What we have here is, well, it's kind of simple. Because if I look here, I have an isosceles triangle whose apex angle is delta theta, and up here I have an isosceles triangle whose apex angle is delta theta. So these are similar triangles, which means any ratios that I can make in one of them, the corresponding ratios have to be the same in the other one. So what I can say is if I look at the blue, I can see that delta C divided by R. Okay, in other words, suppose I take the ratio of the base to the equal side. That has to be equal to delta V divided by V. Okay. Now what I'm going to do is I'm going to divide this whole equation through by delta t, and I'm going to rearrange things a little bit so that I get delta v over delta t is equal to v over r delta c over delta t. Got it? But delta v over delta t is the average acceleration. So we're almost there, but we don't want the average acceleration. Okay, we want the instantaneous acceleration. So we have to look at this thing as delta t becomes very, very small. So now we let delta t approach 0. And I want you to focus your attention on delta c over delta t, and I want to have you ask yourself, what is delta c over delta t? Well, it's nothing in particular. It's this length, which is just this length. Okay. What's really important to us is what delta s is, because what I know is that delta s over delta t is equal to v. Okay, because delta s is the distance which this object has moved, and delta t is the time it took it to go that distance. And so technically this is the average velocity, but in fact we know that the velocity is constant, so the average velocity is the velocity. So the velocity is delta s over delta t. Unfortunately, that's not what we have here. We've got delta c over delta t. But delta c is pretty close to what delta s is. And if you imagine now cutting delta theta in half, delta s and delta c are going to get closer still. And imagine cutting it in half again, and they're going to get closer still. And so what we find is that v over r times delta c over delta t approaches v over r delta s over delta t as delta t approaches 0. And so what we finally find is the acceleration of this particle is equal to v squared over r. And your author denotes this as a sub r, which is r is for radial. This is the radial acceleration. Its name normally is called the centripetal acceleration. Excuse me. Okay, so centripetal acceleration. Okay, I want to give you all a little Latin lesson. You all have heard of something, you probably never heard of this before, okay? But what you have heard of is a word called centrifugal, okay? That's not our word. Our word is centripetal. There is no such thing as a centrifugal force, okay, in spite of the fact that you all have heard of it, okay, and maybe later in the semester we will talk some about what are called fictitious forces, but in the real world, the centripetal force is the one which is the real thing, and so where do these words come from, and how can you remember which is which? Well, what centripetal means, well, centra, I think you can see what that means. That refers to the center of the circle. Petal, that comes from the Latin word peto. I'm sure some of you are taking Latin. Peto means I seek. So a centripetal force is a center-seeking force, whereas centrifugal, F-U-G-O, fugo, is the Latin word for I flee. Okay, and so the centrifugal acceleration is a center-fleeing acceleration, which in fact would not have this particle going in a circle. Okay, so that's the basics, and now let's end this video and then do some examples.